In this video, we will learn about circuits and how they create a magnetic field and force on objects around them. To start off, we need to learn about Ohm's law. Ohm's law states that the current through a conductor between 2 points is directly proportional to the voltage across 2 points. In other words, the current I is equal to voltage over resistance. Current is measured in amps, which you'll see as a capital A. Voltage is measured in volts, and you'll see this as a capital V. Resistance is measured in ohms, which is this little half circle symbol. So an important relationship to understand between these variables is that as current increases, voltage increases. If current were to decrease, resistance increases. Those are important relationships to learn between these variables. So when we see a circuit, it'll generally be drawn a little something like this. Obviously, this is a very simplified circuit. So we see here, we see two lines. This is the battery, and it has two lines because the longer side is the positive side and the shorter side is the negative side. An important thing to know is that when current runs, it runs from the positive to the negative. In other words, in this specific circuit, the current will be running from this to here. It'll eventually come back around here and finish up at the negative sign again. These little spikes that we see right here are the resistors. Now, resistors really work to slow down the current or take some of the power away from it. A really great analogy to put this in terms is a roller coaster. So let me redraw this for us. Okay, so if we think about a roller coaster, the track itself is a lot like the wire itself in a circuit, right? And current is basically a bunch of little charged particles flowing all in the same direction. So in this instance, the people is the current. The people are a bunch of charged particles moving along the track, moving along the wire. So we'll make current is the people in this analogy. And the volts is supplied by the battery. It's what pushes the current through the wire, and in this case, it's what gets the people going around the track. So the volts can be thought of as the carts. And then when you're on a roller coaster, you may have noticed that after a really fast pace around the loop, the roller coaster will kind of slow you down. So those little mini brakes we can think of as the resistors. All right. So when you're on a roller coaster, many of you have probably been on one, when you're on a roller coaster and you're moving real fast, you notice there's a lot of wind around you. If somebody were to stand, say, maybe right here, they would feel the wind as this cart came down and around this loop, right? But if somebody were to stand over here, they may not feel the wind. So in other words, you have to be within a certain vicinity or near the coaster to be able to feel the wind that the coaster creates. This is in turn a magnetic field. A magnetic field is a region around a magnetic material, in this case the track, or a moving electric charge, the people, within which the force of magnetism acts. So how close do you have to be to the magnetic material with the current flowing for it to have an effect on you? It's an area. Magnetic field's an area. Important thing to note is that magnetic field is also commonly referred to as B field. Okay, so B field is measured in Teslas, capital T as we see right here. And when it's denoted on the page, it's either in X's or dots or O's. The X's mean that the B field is going into the page, and the O's or dots mean that the B field's coming out of the page. Because remember, B field's an area, it's not a plane. A way to keep track of this and kind of how the B field interacts with the current and the forces created by this is called the right-hand rule, as we see in this picture of this hand down here. So when we look at the right-hand rule, you want your fingertips to always represent the direction of the B field or the magnetic field. Your thumb always represents the motion of the current, and your palm always represents the force coming out of it. So in this resistor over here, if we were to practice on it, we would draw, let's say, let's make those a little bit better. We would say if this was the B field right here, right? The B field is going into the page. So if you take your right hand, your fingertips should be pointing at the screen. And in this, on the right-hand side of this circuit, the current's traveling down, right? Because it's going from positive to negative, so it's traveling down. So if you're to orient your hand so that your fingers are pointing at the screen and your thumb is pointing down, you should get that your palm is facing to the right of your body. So the force is going to the right. However, just like on a roller coaster, when you're moving slower, there's not as much wind. When you're moving faster, there's more wind. The B field is constantly changing. So if we were to take the B field of the top part of the circuit, which is this part right here, we would say that you point your fingertips at the screen because the B field's going in. However, the current's going to the right, not down. So your thumb would be pointing right, which means that the overall force, your palm of your hand should be facing up. And if you follow this around, if you follow the current around and rotate your thumb accordingly, you will see that all of your forces end up like this. And so in this specific circuit, since the B field is consistently in the page, it's consistently in the same direction, the forces that it creates all cancel out because we have a top and a bottom, a left and a right. So in this circuit, there's no net force. Okay? So when we put these two concepts together, we get Lorentz law. Lorentz law is the combination of electric, Ohm's law, and magnetic force, the magnetic field, on a point charge on the current, the people, due to electromagnetic fields. Lorentz law states that the overall force is equal to the current times the length of the wire times the magnitude of the B field, in our analogy, how much wind, times the angle between the B field and the wire. So in our example above, we had the B field like this. However, remember that B field is an area. So we're seeing the front plane of the B field. If we were to look at the top plane of the B field, we would see this. And if the circuit is coming in like this, we would see in this picture, we would see, so this might be the resistor, we would see the top part of the circuit coming in, right? These two intersect perpendicularly, and when something intersects perpendicularly, it makes a 90-degree angle. Now, of course, if the circuit intersects the B field at a different angle, you'd have to find that angle, but for this specific problem, we'll use the 90-degree angle. Okay, so let's try and apply all of this to a practice problem. The right edge of the circuit in the figure below extends into a 50 milliteslas uniform magnetic field. What are the magnitude and direction of the net force on the circuit? So right off the bat, we know that we can use our right-hand rule to find the direction of the net force. So we see here that these are x's, which means our fingertips should be pointing to the screen because the B field is going into the page. And on the right edge, it's important to note that it says the right edge, the circuit is going down. So if you were to orientate your thumb down with your finger still at the screen, the force, your palm, is pointing out to your right, just like in the example we showed before. So we know that the force is to the right. Now in the example above, there was no net force because we assumed that the B field was acting on the entire circuit. In this specific example, the B field only acts on the right side of the circuit, not the left, so it won't cancel out. However, the top and bottom do cancel out. Now to find the magnitude, we need to start by writing out all of our known values. So we know that there is a voltage of 15 volts, a resistance of 3 ohms, a length of the wire is 10 centimeters, which if we convert is 0.1 meters. And the B field magnitude is given at 50 milliteslas. If we convert, we would say 50 times 10 to the negative third teslas. Now we don't have the current. So to solve for the current, we can use Ohm's law, which we learned earlier in the video. Ohm's law states that current is equal to voltage over resistance. So we will do current equals 15 volts over 3 ohms, and we will get a current of 5 amps. Okay. Now if we remember, Lorentz law states that the force is equal to the current, which we just found, length of the wire we're given, the B field magnitude we're given, and sine theta. And of course, this is just how we explained earlier, the angle is 90 because they're intersecting perpendicularly in this case. So from here on, you just plug in your values. So we will do F equals 5 times 0.1 meters times 50, 10 to the negative 3, sine of 90. And when we plug all of this in, we get that the force is 2.5 times 10 to the negative 2 newtons. So our final answer is that the force is 2.5 times 10 to the negative newtons to the right.